in this 1 hour focused Rust bootcamp, the first thing that you should do is to install Rust. And by the way, in this bootcamp, I will not try to convince you to learn Rust, because if you're watching this, probably you are already convinced. I will leave this link in the description in case you want to install it right now. But once you have it installed on any machine, you can follow along with all the examples. You can just Google install Rust and you should end up in a page that looks like this. Be sure to install it. You can also use this Rust app tool, which is very good. And you should end up on something that looks like this. To check the version, you can type rust c --version. Rust is a compiled programming language. Rust C is the compiler and Cargo is the package manager of Rust. So if you have this Rust C and Cargo, you should be good to go. I'm using WSL, so I'm using Windows Subsystem for Linux. Let's start with a very simple hello world, because this step is very, very important. I will create a new folder. We can call it Rust Live. We step into this folder and let's open this with any IDE you want. VS Code, Cursor, Anti-Gravity, whatever works for you. And I'm here in an empty project. Let's create a file and we will call this file main.rs. RS is the extension for Rust files, Rust projects, and I want to create a hello world, and the hello world in Rust is done like this. We have a function main with this print ln exclamation mark hello world. And now you might think, okay, how can I run this file? There is not like a play button or something like that. To run this project, you need to compile this file. How can you compile this file? No, not cargo run, but rust c and the name of the file, main.rs. We'll do this just once, compile the code. And if we refresh here, we should see an executable here. Now, since we are in WSL, we don't have a .exe, but we have an actual Linux program, okay? And to run this one, we should type /main. And we have hello world. We used just the Rust C, the Rust compiler. And this is something that usually you don't see in the tutorials. Now I want to make some change on this file. For example, I want to add a crab here. I save, and then again I try to execute this /main. But nothing changed here. I saved here. Why this didn't work? Recompile it, right? Rust c main.rs again /main, and now we see the changes. And this might not be ideal, because every time I make a change I need to compile all the files and then I should run this again. I've done this just because I want you to understand what Cargo does behind the scenes. So let's close this project and now let's initialize a Rust project like you usually do. Usually you use Cargo. And by the way, I want to mention that there is a website called crate.io, which is basically NPM. If you want to explore it, it's very similar to NPM. Let's initialize a new project using Cargo. Cargo new, and the name of the project. For example, I don't know, Rust Live 1. You should see this creating binary and the node. We step into this directory. We open this with any IDE we want. We should see something like this. Now, this is similar to what we had before, but there are some differences. Here I see an src folder, and inside this we have a main.rs file. It's the same code that we had before. We have also a .gitignore because we initialized a Git repository. We also have a cargo.toml file, which is very similar to a package.json or requirements.txt for Python. And we have here the package, the name, version, In addition, if you have the latest version of Rust, here you should read 2024, and here we'll add the dependencies. How can we run this project now? This time is cargo run, because we used the cargo to initialize it. And we have this, okay? Quick tip, if you don't want to see every time this compiled, finished, and stuff, you can do cargo run -q. Usually I like this one, especially for tutorials. So you have the exact same output that we had before. Let's change here the code. For example, we can add some crabs. I save cargo run. And this is the difference. If I use cargo, cargo is compiling all the files for me. Thank you so much, cargo. But in the first example, we compiled this manually. This is very important to understand. If you didn't know about the -q option, write this in the chat. Also in these examples, I always use cargo run -q, which stands for quiet. Something else I want to mention is that there is another way to create Rust projects, which is this one. Let's say that I have a new folder. I create a project, I call this Rust Alive 2. I step into this directory. I am in an empty directory. Let's say that I want to create a Rust project here in this folder, because cargo new creates a new folder, cargo init, and it creates a Rust project right here. I'm not opening it, but it's the same structure. Cargo new, it creates a folder. If I want to create a project here, cargo init. Okay, and this was basically the hello world. Now we can start the real bootcamp here. This repository is available for you. I highly recommend you to follow along. I will type some stuff here, but we also have the repository on GitHub. Before we start, there is this hello cargo. I will not run this one, but I want to quickly mention the comments in Rust. Very easy. We have // for a one-line comment, /* for a multi-line comment, and // for the documentation. Be careful here, especially if you are a JavaScript developer. I really focused this bootcamp for all the pitfalls and strange stuff that happens in Rust. Variables, they are declared using the let keyword. Be careful. And we can see here this, let x equal 5, and then we print this variable. Usually in Rust we print these variables with these curly brackets and then the name of the variable. Rust is statically typed, so the compiler needs to know the type at compile time, but most of the times it can infer the type. It can basically imagine the type. Before we keep going, I want to quickly mention the extensions I'm using here on VS Code. We are using the Rust Analyzer. This might create some spoilers, but it's fine. And the other one is Even Better Toml. Before there was an extension called Better Toml, now we have Even Better Toml. If you have been writing Rust stuff when we had just Better Toml, you have been writing Rust code for a while, but use this one, Even Better Toml. Let's run this project. And you can see here that the value of x is 5. Okay, perfect. Now I want to try to do something super simple. I want to change the value of this variable. So x equals 6. This is absolutely valid, for example, for JavaScript code. Bam. Error. What? Cannot assign twice to immutable variable x, but I used let. This is what a JavaScript developer would think. And this is also an excuse to let me introduce you the Rust compiler, that it's very annoying, but it's always on point. Let's read the first assignment to x here. Cannot assign twice to immutable variable. And it's suggesting to add this stuff. Check how the Rust compiler is super clear. You see these green pluses. Okay, let's add this mute keyword. I don't think there are other languages with this mute keyword. Let's try again. And now it works. By default, the variables and everything else basically is immutable in Rust. And the variables, of course, they exist only within their scope. The scope is like these curly brackets. So be careful about this. Then there are constants in Rust. And someone might say, why constants if all the variables are immutable by default? There is something, and the constant still, they make sense. They are declared using the const keyword. They are always immutable. So if I read the const, I don't have to check, is there the mute keyword close to the let? No, they are always immutable. Writing const mat doesn't make sense. So const is just const. An important part is that if you define a constant in Rust, you need to define the type. You see here it's gray because the Rust analyzer is helping me, but I didn't write this I32. In the constant, I have to specify the type. If I try to don't specify the type, the compiler will complain. And also, the name should be in uppercase with underscores. And also, we need to define the value of this constant, basically an assignment, when on the declaration. On the variables, for example, I can do something like that. Let mute x and then x equal 5. This is acceptable. If I try on the constants to define this and then do this on the other line, it will complain. And during the compilation, this will be replaced in all the places in the code. Let's do like this. The value of this constant is 100,000. In Rust you have to be explicit. Another very important concept is shadowing. What is shadowing? Shadowing is when we declare a new variable with the same name in the same scope or in an inner scope. Shadowing is called like that because we're basically hiding the old variable. Let's see an example because it's easier. Check here on line 12, let z equal 5, okay, we print the value of z, it's not immutable, and then here, check line 16, let z equal z plus 1. We are defining the same variable again, and also, this is very interesting, we can use the previous value of z to define the new value. And this is where things really become interesting, because here I can have an inner scope. Check here on line 21, when we define another z equal to z multiplied by 2, we print it, and then we go on the outer scope again, and here again we will have the value that we had on line 16. I want to run this part. You see, the value of z is 5, 6, 12, and 6. Someone might say, okay, so shadowing is similar to mutability. No, it's not. it's different. What is the main difference between mutability and shadowing? The main difference is in the type. We can see, for example, here a variable called spaces, which is of type, let's say string for now, that is basically 3 empty spaces. Here you can see this empty string here. We print this variable and then check on line 32. Let spaces again, we are shadowing, of type usize, basically a number, spaces dot len. So we define the new variable based on the previous variable dot len, which is a function basically to get the length of this string. But this is a different type. Okay? You see here, if I try to do something similar with variables, we are here on the variables example, let's say with x equal 5 and then x equal hello, this should not be possible. I can't do this because mutable is about the value, not the type. Okay, this is something which is very, very important. Expected integer, found string. Okay, Rust compiler. I really love the Rust compiler. Let's talk about primitive types. I think that in Rust we reached perfection in the definition of primitive types. And if you come from JavaScript, in JavaScript it's really a mess. Primitive types, they represent a single value. There are 4 main types: integers, floats, booleans, and character. Rust is statically typed, so the type must be known at compile time, but this type can be inferred. Let's see them all. Integers. signed and unsigned in 8, 16, 32, 64, and 128-bit sides, I sides and U sides, which depends on the computer architecture. The default is I32. We also have U64 here, and we can use this underscore as a visual separator. If you've been following along, you checked that I already used that in the constants. Okay, here, floating point numbers, F32, F64, single precision, double precision. F64 is the default float type. Perfect. Booleans, bool type can be true or false. True and false not capital, so be careful if you are a Python developer, because here we have true and false not capital. Okay. And the last, character, can be a char in single quote, single letter. It supports Unicode, it supports emojis. That's it. This is perfection for me. This is probably also because Rust is quite new compared to other languages that have different types. It's weird. Perfect. Primitive scalar types. Amazing. It's so simple that it's mind-blowing. Be careful here. Arrays, be careful. Key concept of arrays. Arrays groups multiple values of the same type. Okay, we can all agree with this. In some languages it's like that, but check this one. Arrays have fixed length. What? The size cannot change of an array in Rust. Arrays in Rust are of a fixed length. They can change the length. One might say, how can we have dynamic arrays? We have them, but the arrays can't change the size. The type is annotated in this way. For example, I32 and 5, check line 12. We define an array of I32 elements, and there are 5 elements. 1, 2, 3, 4, 5. This is a way to declare an array. We can initialize an array if we all have the same numbers, like this. For example, we can have this let be 3 semicolon 5, and it's the same as typing 3, 3, 3, 3, 3. Now we can access the first element with a square bracket 0, a square brackets 1 for the second element, usual stuff. I want to run this one just as an example. If we go out of bound, of course, we will get an error. We should get an error, right? Error, this operation will panic at runtime. Okay, so it will not even allow me to compile. You can't. I also want to mention another important primitive type, which is tuples. This is a concept also for other programming languages, but let's read how tuples are in Rust. They are used to group multiple values of different types. They have a fixed length, the size can't change, and we can access the elements with this dot number notation. Okay, they can also be destructured to get all the values at once. For example, check line 10. We can define a tuple called tup, not very original, but it's fine, which has as types a string, an F64, and a boolean. And we can define this like this. This is very useful, especially as for example, as a return type of a function. We can structure the tuple in this way, in individual values, like let x, y, z equal tup, and then we can, for example, print them and access them with the element by index. For example, tup.0, tup.1, tup.2. Let's run this one. Perfect. We are warming up. By the way, I'm super excited about this 1 hour focused lesson. And now, a very important one, of course, is functions. Key concepts of functions. They are defined using the fn keyword. Probably you already noticed that. They have a name and they can take parameters. They can or cannot take parameters. Very important, the parameters must have their types declared. This will not be inferred. And they can also return a value. We will see the syntax soon. Be careful here. I'm sure that most of you already know what a function is, but let's see functions in Rust. We have a normal function here with no parameters and no return value. This is a function that takes one parameter, you see an I32 in input, a function with multiple parameters, for example here a value and a unit label, a char, and then this is the important one. Check this out, because this is different from other programming languages, so be careful here. fn add 5 takes a number in input and it returns an i32. Okay, makes sense. But then here, check this code. Num plus 5 without a semicolon. What? I'm sure that some people are more used to this syntax. Return num plus 5 semicolon, right? In Rust we have the implicit return, and if we type return num plus 5 semicolon, it works, but usually if we want just to return something at the end of a function, we don't type return. Return is usually used for early returns, or if we have a cycle, if we have a reason to type this return. Otherwise, just like this. I'll also use this syntax in this bootcamp. So this is the thing you have to be careful about. For example, we have now this function main, and we can call the functions like we do in other programming languages, same stuff. An important part is statements and expressions. Statements are instructions that perform some actions and do not return a value. For example, let x equal 6 is a statement, okay? An expression is something I can use as an assignment, and a function call is an expression, especially when it has a return type. You can have, for example, let sum, which is a variable, equal to this function, and this will get the value that is returned by the function. You're not even getting started. The funny part will start in 2 minutes. Okay, and here we see the output of function. And now, the interesting part. I hope you are all ready. Because yes, in this bootcamp, I will try to explain ownership in just 20 minutes. I will not bore you as much, but you need to focus now, okay? I know, what F is ownership? Perfect. Okay, ownership in Rust. Ownership, you might have heard about it, is the Rust most unique feature, because it has a very deep implication on how the language does work. So you need to be very, very careful now. Trust me. Ownership enables to make the memory safety, the famous memory safety in Rust, without needing a garbage collector. And it's really important to understand how the hell ownership works and also what is that. Let's talk about memory handling. All the languages must manage how they use memory while running. Okay? We have two main approaches. Approach number one, we can have a garbage collector. It's basically a sort of mini program that regularly looks for no longer used memory as the program runs, and it just cleans the program. What is the downside of a garbage collector? It freezes the program. Oh my god. And maybe you never notice it, because maybe you've had to do with some small programs, but the fact that the program freezes while it's cleaning, it might be a real problem when we have to do with performances. So someone might say, okay, we don't need a garbage collector, because we never needed that, because if you wrote C, C++, or assembly code, you don't have a garbage collector. In my opinion, this is even worse, because you need to allocate and free the memory manually. And this is basically the nightmare for all the developers. If you ever had to use alloc and malloc in C, write this now in the comments, in the chat. I am one of you, of course. Rust is different, because the memory is managed through a set of rules that the compiler checks. And if any rule is violated, the program will not even compile. And the most important part is this one. Ownership will not slow down your running program. So ownership, it's much closer to approach number 2, but without having to do this really manually. Ownership is a new concept, and I think the most senior you are as a developer, and the harder it will be to understand, because it's like a new concept. If you are a new developer, probably it will be easier for you to understand ownership. Ownership is this new concept, and it's a way to develop code in a more safe and efficient way. Probably I will have to fight a bit with the compiler, but once I get used to it, it absolutely makes sense. We will make an example soon, no worries, and we'll use a data structure called string with capital S soon, okay? But now I need to annoy you for 5 more minutes. You need to resist for 5 more minutes. I need to talk about the stack and the heap. And maybe you never heard about them, because many languages don't even require you to think about what is the stack, what is the heap, what is this. In Rust, in this language, if a value, a variable, goes on the stack or on the heap, it affects how the language behaves with that variable. And this is why many people are confused about what the hell is going on when we have to learn ownership, because they skip this part. They skip understanding what is the stack and what is the heap. Both the stack and the heap are parts of the memory available, and I'll try to explain you in the easiest possible way what is the stack and what is the heap. What is the stack? The stack is like a pile of plates, okay? The stack stores values in order it gets them and removes them, the values, in the opposite order. This is also called LIFO, which stands for last in, first out. We can push new plates on top of it. We can remove the first plate from the stack. This is what is allowed in a stack. A very important part is that all the data stored on the stack must have unknown size and a fixed size. The data with an unknown size, yes, there is some data with unknown size at compile time, or that might change, can't be stored on the stack. In this case, we need to use the heap. And what is the best analogy for the heap? I've been thinking for a while for it. The best analogy with the heap is when you have 2 more friends and all 3 of you go to a restaurant. Okay, what will happen in that case? You'll probably get a table with 4 chairs. Okay, why? Because the heap is less organized. It's just that I want some space. I don't even know how much space I need. Some friend might come later, okay? There is something called the memory allocator that does 3 things. It finds a big enough empty spot in the heap, like the waiter chooses a table. It marks it as being in use, people just sit on the table, and it also returns a pointer, a location's address, the number of the table. And this process is called allocating. And where is this pointer put? On the stack, because the pointer to this variable or whatever has a fixed size. And to get the data, we just follow the pointer. The waiter already knows which table has which number, but this is the best analogy I can make. All the slides are available. The stack and the heap. The stack is for element data structures that have fixed size and are known at compile time. What goes on the stack? What we saw a couple minutes ago. Primitive types, integers, floats, booleans, characters. Fixed collections, arrays, and tuples when the tuples has just elements of this type, of course. And also all the pointers, metadata, and things that have a fixed size. The heap, instead, is for elements that have a variable size, and it's known at runtime. And this is owned by ownership. What goes on the heap, there is a spoiler here, dynamic collections, strings, vectors, hashmaps, linked list, everything that we don't know the size at compile time, and also boxed values. I will not talk about smart pointers here, but I want to just put these boxed values. I have a video about the smart pointer box. If you're interested, we will not cover this in this bootcamp. Pushing and allocating. Pushing on the stack is fast. Allocating space on the heap is hard. Accessing data on the heap is slow. Accessing data on the stack is usually fast. Okay, so someone might say, okay, so what's the point for the heap to exist if everything goes so well with the stack and it goes so slow with the heap? Because sometimes we have some data structures that we don't know how big they are. Think about getting an input from a user, a string from a user, or maybe we have a dynamic array and we don't know how big this will be at runtime. Okay, also the stack has a limited space. And also when you call a function, the values are passed into the function and the function's local variables, they get pushed onto the stack. When the function is over, the values get popped off the stack. Now, this is the most important part. Be careful now. Ownership's purpose. The primary purpose of ownership is to manage the heap data. The primary purpose of ownership is to manage the heap data. Keeping track of what code is using what data on the heap. Minimizing the amount of duplicated data on the heap. Cleaning up unused data on the heap. Ownership is to manage only the heap data. I hope that was clear. Ownership rules. Each value has an owner. There can only be one owner at a time. When the owner goes out of scope at the end of the curly bracket, the value will be dropped. And if you don't get this reference, you should check this movie. And now it's time for a demo. Okay, I annoyed you enough with some slides, but I hope that was clear. I put a lot of effort to try to put the simplest possible examples about ownership here. Okay, so stay with me for 5 more minutes. We will go back to the funny stuff later. Ownership and moving. Each value has one owner. When the owner goes out of scope, the value is dropped. So now let's see this example. Let me know if you think that this example would work or not. Let x equal 10, let y equal x, so y is equal x, and then we print first y and then x. Of course, it should be print y equal y. This is just dumb stuff. Okay, let's do it. Let's try. It worked. It worked. So who said no was wrong. Okay, let's try another example now. I love these examples with ownership. Let s2 equal s1, print ln s2 equal s2, print ln s1 equal s1. Will this work or not? And why? Someone said yes. Okay, let's try. Bam. No. 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 What the hell is going on here? What the hell is going on here? Borrow moved value s1. Let s1 string move, of course, because s1 is type string. Type string. Value moved here. Value borrowed here after move. What the hell happened here? I'll show you with some slides that I prepared, okay? Because it's easier to understand. And also we need to understand the difference. Why did it work with the numbers and it didn't work with a string? This is where people get really confused about Rust, but they should not be. In the first example, when we used a number, it was 10, but whatever, I kindly remind you that types such as integers, known as size at compile time, they are stored entirely on the stack. So when the copies of the values are done, they are very easy to do. And there is no reason to prevent x from being valid after we create y. They are both on the stack. They should both be available. Rust has a special notation called copy trait. Basically, when we use the equal, we make a copy of that value. And who implements the copy trait? The general is that any group of simple scalar values, do you remember the ones I introduced? The arrays, Booleans, Char, tuples that contains primitive scalar types, values, integers. They don't use the ownership. You can use these. You can use them as we do them with most of programming languages. This part is very important. What happened with the second example? We had this S1 here, and when we type S2 equal S1, it happens something like this. This is the first step. Okay, so the new S2 points at the same location that S1 was pointing. Someone would expect that we had something like this. If Rust copied the heap, that we had something like this. This is what is usually called a deep copy, copying not just the pointer but the whole structure. Instead, what happens is this. S1 became invalid and just S2 is valid now. Why? Why S1 is not valid anymore? Why S1 has been invalidated? I still want to use S1. I remind you this one. Ownership rules. Each value as an owner, there can only be one owner at a time. There can't be two owners. This will generate so many errors. S1 might go out of scope, but S2 is still not out of scope. This would be a mess. S1 is just not valid anymore. Can we solve this thing? Yes, we can, with something called clone. Clone is to make a deep copy. So if we want to have this behavior, like a deep copy, we can call this clone. This works fine and the heap data gets copied. We have to be careful because here the code might be expensive. I hope this is clear for at least some of you. Here on line 20, I can type .clone. Like this. I can try this again, and now it works. Now I can just clone everything. No, that's not the idea. Now you have to be very careful about this example, because some people might say, okay, but I will never do S1 equal string and then S2 equal S1. Okay, I promise. This is not like a normal use case. Okay. Check this example. No, don't clone everything. We have a function that calculates the length of a string. In input, we have a string S, and we return a usize, basically a number. In here, we define a variable called len, that it's basically s.len. This is a method of strings. We print it, and then you see we return here the len without typing a return len semicolon, but just a len. This is not a type. And now we try this. We define a variable called s3, for example, Rust, very original. We calculate the length. Let's calculate the length of this. Be careful here now. Consumed string length 4. Okay. We have this string from Rust. We calculate the length, and this does work. Okay. Now, what if I want to just, use the variable after this? Bam. And this is where I almost wanted to stop using Rust. Okay, listen this very carefully. I create a variable. I use this variable in a function, then I can't use the variable anymore. What? You can agree that this is a quite common use case. I create a variable and then I want to use this variable in a function and then probably use this variable again. The function takes ownership. Now the function basically stole this variable from here. I had really a mind-blowing moment here. I know what we are thinking. You are thinking, okay, let's just... This was for fun, of course. Let's just clone. Every time I have to call a function, I clone the variable on the heap. I make deep copies like this. No. No, we need another way to do this. We need to solve this problem. Okay. Borrowing and references. There is a solution to this. You just have to be patient for 5 more minutes. What is a reference? References and borrowing. First of all, we introduce them using this ampersand, and we have references for basically all the types. For example, a reference to a string can be of type ampersand string. This is a reference, and it allows to read exactly to what we had in our mind, to refer to some value, but without taking ownership. I just wanted to read the value to calculate the length of the string. I don't want to just like steal your ownership from here variable. I just want to use it. We have this s of type ampersand string or at string or whatever, and this ampersand s1 creates a reference to s1, but it doesn't own it. This is exactly what we need, and so we need to make a slight change to this function, and then everything should work. The action of creating a reference is called borrowing, because I want to just, borrow the variable for a while, but this will not be mine. I just want to borrow. At any given time, you can have one mutable reference or any number of immutable references. We'll see an example soon. And of course, the references must always be valid. Let's go back and let's try to understand this reference thing. Borrowing creates a reference to a value without taking the ownership. Okay, so we have here the same function that we had before. To be honest, it's not exactly the same function. This is the function that we had before, and this is the function that we have now. Calculate length, but here we don't have here s string, but s ampersand string or at string, and we return a useId. This is the only difference, is this small ampersand here. Let's see the same example that we had before. We create a string, in this case it is hello. We calculate the length, but this time we will pass a reference here, ampersand s1. We print the length, and then we try to use s1 again after this. Let's try it out. It works. I can still use s1 after calling a function. I hope that this was clear. This was the simplest example about ownership and borrowing. I also have other videos, longer videos, but this is specific for this bootcamp. What is a mutable borrow? We borrow s2 mutably to change it. When we take a reference, we can also make some changes to that variable. That sounds not that counterintuitive, but this is how it is. Of course, the variable has to be mutable. We can print this before and after the change, and we can invoke this function change at the end. This function change basically it concatenates to another string. This is similar to like s1 plus s2. Okay, let's see what happens here. And you see we have before the change, this string is hello. This s2 variable now is hello world. It's not just something in the scope of the function. The function changed s2 because it's a mutable reference. You can have many immutable references. Immutable references it basically means I just want to read the value, but I don't want to change it, like we had at the beginning. So for example, we can have multiple immutable references because more than one is reading them, and as soon as rn1 and r2 are no longer used, we can also have one more mutable reference. Immutable is when we can change the value of the variable. Want to execute this part? This does work. You can't have two mutable references. Can you understand why? I can't have two mutable references, two references that can change the value. If I have two references that can independently change the value, we'll have some problems, of course, race condition, of course. And also I can't have a mix of immutable and immutable references. Once I have a mutable reference, I can't also have immutable references. This will throw an error. I want to check if this throws an error. I can't have immutable and mutable references mixed. The last thing about borrowing is this one. Let's imagine that we have this function, okay? A function called dangle. That's not very promising. That returns an ampersand string. Yes, we can even return these references, but check this code here. We define a string, and then we return the reference of the string. Is this allowed or not? No. Here s goes out of scope. You remember the rule number 3. So the reference would be dangling. So the compiler is basically protecting me from doing this. Control flow. We should be used to all this stuff, but there are some little things that you should know. I highlight what is different based on other programming languages. Key concepts of if expressions. They are used for conditional branching, not strange here. The syntax is if condition, block of code, else if condition 2, block of code, else. This is interesting. The conditions must evaluate to a bool. There is not like magic change or cast. No, it has to be a boolean and it must evaluate to a bool. Interesting part is that if is an expression. Let's see this with the example. We have this basic example of the if here. We have a number, if, print, else if, else. If is an expression, what does it mean? I can do something super cool in Rust like this. Let x equal if. Because if is an expression. Based on this condition, I can assign two different values of on x. The number is small, the value of x from the if expression is 6. If I change this to true, it's 5. Let if is allowed in Rust. The important part is that all the branches must return the same type when used as an expression, of course, otherwise this is not allowed, because if I type here, the compiler, I think, will get angry, no? Because otherwise I can assign two different types on the same variable. This is not allowed. So they have to be the same type. I can't cheat, okay? This is interesting. There are 3 loops in Rust. In Rust there is a loop called loop. Quite funny, don't you think so? Key concepts of loop. Basically a loop is a while true. Basically, it creates an infinite loop. We can use break to exit the loop. Interesting thing, we can return a value when we are using the break statement. We define a mutable variable, of course mutable, otherwise we can change it. And also the loop is an expression. We can type let result equal loop. We have all of these, and then when we break, for example when the counter is 5, we return what? Not the counter, but counter multiplied by 2. A super powerful way to code, I think. Let's do this. Bam! 1, 2, 3, 4, 5, 10. Like if I read the loop, okay, this is a while true. Understand this in a fraction of a second. While loops, not much to say here. We have while loops in Rust. It repeats code, the condition is checked before each iteration, and you can use the break. Okay? 3, 2, 1, lift off. Okay? Nothing strange here. For once, Rust acts normally. Key concepts for loops. They are used to iterate over collections or ranges. The syntax is for variable in collection. Let's see an example. Here, this is an array. Usually we can iterate over this collection. An array is a collection. And you can do this in different ways, but a good way to do this is by using an iterator. Otherwise, we risk to take ownership with a for statement. We usually don't want to take ownership with a for statement, so this is a good way to do this. For element in a dot iter, we print the element. We can also have a for loop with a range. This is very similar to what we do in Python. For number in 1.for and also .rev if we want to do this in reverse. There are also plenty of methods here. I use the reverse because you might use that one. It's a quite common one. Value is 10, 20, 30, 40, 50, 3 to 1, and the lift off. Again, structs are custom data types that groups values all together. They are defined using this struct keyword and a name, for example user, and each field in the struct has a name and a type. We can create an instance using this let and the name of a variable and then this user, and you can access the fields with dot rotation. But let's see an example, it's easier. Check the syntax here. Struct user, username, string, email, string, sign-in count, u64, and active bool. But there is also something called tuple struct or struct tuple with unnamed fields. If we don't need a name for the fields, we can have this tuple struct like this. For example, here we have a struct color, i32, i32, i32. We all people understand what's going on here. We'll have 3 numbers for RGB, and yes, we can add some additional checks, but it is what it is. We have this function main, and here we can also use this shorthand called the field init shorthand for the email and username. Check it out here. We define a string called email using this string. We define a username with a string like this, and when we create this, we can have let mute user1. Yes, the struct instances can be mutable with an email, a username, active true is defined here, and sign-in count is 1 and is defined here. We can access the fields using dot notation, this is like in JavaScript, and if the instance is immutable, of course, I can change the value. But a cool, interesting part is that in case I don't want this to be changed, I just have to omit the mute. Let's try this. Okay, the Rust compiler is complaining because I'm not using the email and sign-in count. Okay, username is some user 123, and after changing it, we have another user 456. Okay, there is also a struct update syntax. We can create, listen, this new instance using some fields from an old instance. So for example, we have this user2, and we have an email and a username here from this inline string. We can also do this like this. And let's say, okay, all the rest of the values of the fields are based on user1. It's like a default. We have this dot notation. And then, of course, we can print the user2 username, and also the user1 sign in is copied. We can create an instance of this tuple struct in this very simple and beautiful way, and then we can access by index using dot notation as we usually do with tuples. Let's try it out. And we have username, new username, struct update syntax, and create an instance with this tuple struct. Enums define a type by listing its possible variants. Enums in Rust are super powerful. A value can be one of the variants, but of course not all of them. Variants can do whatever they want. They can store data, they can have no data. Each variant can store different types and amount of data. There is also a very common enum called option T. Let's see an example. We have here a very basic example of enum IP address kind. For example, if we want the IP just to be of version 4 or version 6. We can have another enum, for example, for variants for animals. For example, in this case, you can have an animal which is either a dog, a cat, or a fish, with a string, which is probably the name of this animal. I think a good example for this is this enum message. Someone is asking about this allowed code. This is for demo purposes, otherwise you'll get a bunch of warnings and stuff, but usually you don't have this. I do them to avoid to have plenty of because the Rust compiler is super annoying. I need to limit it in some ways, otherwise you tell me, no, you didn't use this thing, but here I just want to show an example. This is, I think, a good example for enums. Enum message, it can have as variants: quit without any data, move, for example, with a sort of point, x and y, write with a string, and change color with basically a tuple, i32, i32, i32. Then I can create instances based on these enums. We can have 4, 6 for the IP. By the way, we have this strange, weird debug symbol, derive debug. We need to add this sort of attribute here at the top. And here we can create instances. They are super powerful to create models of something. I hope you can read here at the top. Now, I hope you're ready for something a bit mind-blowing. Ready? Rust doesn't have null. Boom. I said it. Rust doesn't have a null, the null keyword. It has an enum called option. Boom. The chat is exploding. Rust doesn't have null. We don't need a null. Why are you still using null? Null is null. Wait, give me a chance, because it really makes sense. We have an enum called option T. T stands for generic, basically any type, and it has two variants. Some with T, the type itself, or none. We don't need null anymore. We just have something which is Option is like basically a wrapper of any possible type, or it can also have the none. We can have this let some number, for example 5, wrapped in this sum, or we can have no number of type none. This is how Rust explains the concept of null. I'm sure people are confused now. I have a whole video about the option enum, single video about option enum. I think you'll find it on the internet. We have this none, but none is just a variant of enum. It's not a keyword. It's a variant of the enum option. The match statement. The match statement is absolutely my favorite one in Rust. And I like many things in Rust, but match statement is the thing I miss the most when I code in other languages. The match statement, it's like a switch on steroids. You can compare a value against a series of patterns. It must be exhaustive, and I'll show you an example now. A switch is like you have different options. It's like an if. Like if number is equal 1, else if number equal 2, else if number equal 3. So switch on steroids. We have the same enum that we had before. We have this function, and the match and the enums, they work so well together. Name a better duo than match and enums, because check this out. Match on this MSG, which is of type messages, based on the variant of the enum, I can execute code. I can do whatever I want here. This is not like a switch status code 200, status code, no. We can do a match based on the object itself. Boom. Think about using this with an HTTP response. I can do whatever I want here. And here I have, based on this variant of the enum, all the variables here. For example, check this out. Message move, I have x and y. I can do stuff here. Message write text, I have here this with a string. This is mind-blowing. And then, for example, we can have this function main and then can process message with different stuff. Quit, move, write, change, color. And these are all handled by the match statement. In case I want to have a sort of default, like a default in switch, I can have here something at the end. It can either be a variable, if I want, for example, say some other number, or it can also be an underscore if I just want to say, okay, I'm not interested into this case. I hope you like the match as I do. And here we can basically do stuff. Now I'll show you something cool, because if you're a developer, probably you know that at some point you might change something. So let's say, okay, the requirements have changed. We have another option here. We don't have just quit, move, write and change color, but we have also another option, a new option, which is a new 8. You do this, you try to compile, bam. Let's read it. Pattern message new option not covered. If you add something on an enum with a match, the compiler will stop me and say, hey, you didn't cover this new option. Do it. Please. This is very powerful, especially if I have to change the code later. We all change the code base at the end, but this will save me, basically. Otherwise, I will get an error here if I have just a switch. I love this. 4 more lessons. Error handling. If you've been reading about the Cloudflare outage, you should read now. If any of you is working at Cloudflare, please watch this lesson. I beg you. Rust has no null or exceptions, but instead for error handling it uses 2 enums, option T and result TE. Option, I already introduced it. Option is for values that might be absent, so it's the replacement of the null. Result is for operation that can fail, an HTTP request, but also something more simple like we do now. And result has 2 types here. You see 2 types. Option is just one because the other one is known. The result is TE. T is okay, is basically the operation succeeded with this value T, which is a generic, and then also RE. So you can have an error, and we can also define the type of the error. We will see this in less than 1 minute. And match is the standard way to handle these enums. Let's see a practical example. The classic function divide, which is a function that might fail. What do? We return a result. Check how beautiful is this one. Arrow result, we can choose the type, of course, result of F64 because it's a division, or a string, which basically will contain the error. If the denominator is equal to 0, we will return a string, which basically will contain the error. Else, okay, numerator divided by denominator. In this main example, we can check a good result and a bad result. For example, the good result is divided 10 by 2. By the way, this is just for demo purposes. Of course, you don't have to have a match for all the variables. It's just to make this more explicit, like this. Okay, good result on this. You can also use the match statement on option. Okay, we can handle this option with the match statement. And here, what is this? What is ampersand? Ampersand some text. Option string. Ampersand some text is a reference. So we got text and we got nothing. So we can handle, for example, option, the null, for example, here. I like the fact that the Rust, yes, it's forcing you to be a good developer, but if you want to go without the seatbelts, it will allow you. There is also something called unsafe for Rust, when basically it removes a lot of checks. If you just want to go alone, it will allow you. If you're not that expert, instead of handling this in a good way, we can just use dot unwrap. So it means basically, okay, let me check what is inside this option. Let me check what is inside this result. I don't care. I don't want to handle this properly. I want to just see the result. I'm sure that this result will work well. And this is basically, this is part of the reason why this happened with Cloudflare. They use this dot unwrap, which basically will just panic the program in case this returns an error or it goes out of bound or something like that. So they should have watched this, literally this part of this bootcamp. This is usually done either if you're sure or if you're a beginner. Okay, just to check. It's like I'm sure it will work. It did not. There is this unwrap that will basically panic if we have numerator 10 and denominator 0. With unwrap, it will basically panic the program. Also, we have another option, which is expect, which is similar to unwrap, but at least it returns this string in the logs in case the program will panic. Unwrap worked, but here, for example, we can read this problem here, you see? At least I can print the log, the expect. But expect and unwrap are very similar. I want to also quickly mention this question mark operator, which is basically a shortcut. If I have this function try divide, something like that, let result divide the other one, denominator, otherwise it can just return an okay result. This is basically to avoid many or nested match statements. Try it out. We're almost done, by the way. I will repeat. Unwrap and expect. In both cases we will panic. The difference is then with the expect at least we have this message. It's like an unwrap but that at least sends a log. We can read at least this error message. Unwrap doesn't have parameters. It just panics. Both of them are bad. Unwrap is even worse. Collection vectors. What is a vector? A vector is a growable, resizable array. So yes, we have dynamic arrays in Rust. Vectors, where are vectors stored? You remember that? On the heap. Because they are dynamic, they are growable. If you understand these two lines, you probably understood ownership, or you are getting closer. Because vectors, they have a growable and resizable size. Heap, of course. So, do we need ownership for vectors or not? Vectors can only store values of the same type. There are some workarounds, but for now I will leave this statement because this is a beginner level bootcamp. Created with vec new or vec exclamation mark. We can add elements using push, and we can access it with either square brackets or get. We will see the difference soon. We can create vectors in this way, and pushing, for example, 3 elements, and we can print it. Honestly, I prefer this syntax more, the one we can read on line 28. The exclamation mark here are macros. Macros are basically pieces of code that are basically can be reused. We can access elements using either these square brackets. We can also use a reference here. And then you can also use this .get function. Which one is better to use, square brackets or get? The get, of course, because the gets, check the definition here, it returns an option. So it can fail in a less miserable way. You cannot have custom macros, so we will not cover macros in this initial bootcamp, I'm sorry. We can iterate over a vector with a for loop, and we can also have a mutable iteration to change the values of a vector. Let's say we have a vector and we want to add 50 to each of the elements. We can do something like this. For example, we can define this vector 100, 200, 300. We can add 50 on each of them. Let's do this. Do you like vectors? I like vectors a lot. They are basically dynamic arrays. We will use them constantly. Collections, strings, key concepts of strings, they are growable and immutable on UTF-8 encoded. Where are they allocated? Where are the strings allocated? Owned. Ownership. Heap. Amazing. They're different from this ampersand str. I'm surprised that nobody asked about this ampersand str. It's a string slice. It's basically just to read. It's just a view of a string. In this case, this can be stored on the stack, but they are not the same. They can be created using string new, string from, or toString. Probably my favorite one is string from, but you can also use see the other ones. We can append using this push str, or we can also push a single character. We can create these strings in these three different ways: string new, toString, and string from. This is my favorite one. And we can also update a string, like in this way. We can append, for example, we have this string foo, and then with bar it should become what you might think, and we can also add one more character. The concatenation is a bit weird with strings. Let's see, the normal S1 plus S2 doesn't work for ownership reasons, so if you want to concatenate with the plus operator in Rust, you have to do something which is a bit weird, which is like S3 equal S1, that takes ownership, plus the reference to S2. We can print this concatenated string. Bam. Empty string, from toString. These are basically all the ways to create a string. You see this foo bar and foo bar exclamation mark with push str and s push. We can concatenate them with the plus, but we need to be very careful about the syntax here. S1 plus ampersand S2. Collection hashmaps. I'm sure that most of you already heard them. So let's see hashmaps in Rust. Hashmaps are used to store a mapping of key to values. It's like a dictionary in Python. They are stored on the heap because they have a dynamic size. Key and values can be of different types, but all the keys must be of the same type, so either all strings or numbers or something like that. We can create a new hashmap using hashmap new, and we can add the key value pairs with this .insert method. Let's see an example here. A very important part is this one. We didn't import some stuff, but we can see here we start to get a bit out of the standard of the normal prelude. So for example, if we want to use hashmaps, I need to add this using the standard library, use std collections hashmap. And we have this function main. We can create a new hashmap. We can insert a couple of things, for example blue 10 and yellow 50, and we can print them. You see blue 10 and yellow 50. We can access a value using, for example, here we define a string and then we use the .get, this one. We can also use a match statement because this get returns an option. Perfect to be used in a match statement here. We can either do like this. We have like a match on this variable here, and you can have some and none. You see how beautiful is this stuff? You see, some and none. I can also execute stuff. Otherwise here I should say, if is null, then I have to do this manually. The match statement on an enum, it forces me to do something on something and do something on none. I hope you can see how powerful this is. Here, for example, match directly on the scores.get read. But this will never fail because we have some and will do something and none will do something. We are forced to do this. I can't ignore this. If I do this, it fails to compile. If I forget to check if it's null, bam, errors everywhere. You see how powerful this is? It forces me to write in the perfect way. How can we iterate over a hash map for key value? It's similar to JavaScript arrays here, in these scores with the borrow, and then you can print them. You can also overwrite a value by inserting the same value again with the same key. In this case, the place it will be replaced. And this is the end of the bootcamp for today. We covered a lot of stuff. We covered many things. All the code will be available on GitHub. We'll have also the slides. You have the links to the installation and the GitHub repository. The links are below. I would like a honest feedback from all of you. I'm happy because we basically made it. So congratulations if you made it until the end. I hope you understood some core concepts of my beloved Rust programming language. Thank you so much. This has been an amazing live event. I hope you enjoyed it, and I hope you learned a lot. If you liked it, you can just make a post, tag me, I will share it. No worries. Give a feedback, and that's it. Perfect. I published this, I think, 2 months ago, the idea, and I think that I achieved the goal of, do some Rust stuff. Really amazing. Bye, everyone.